Hello everyone, welcome to today's video. Today we're going to be covering right triangle trigonometry. So we're going to be looking at the right triangle definitions for all 6 of the trigonometric functions. There's different ways that we could define them. We'll look at the unit circle next, but for right now we're going to look at how we can define these new trig functions using the right triangle. We'll look at some special relationships for 30, 60, 90 triangles and 45, 45, 90 triangles. So they're all right triangles, and if they have the other these special sides, then we can find some special relationships between their sides. We'll look at the cofunction relationships of trigonometric functions. There's some nice properties there. And we'll look at angles of depression and elevation so that we can tackle some application problems. So we will start here with the definition for kind of the main 3 trigonometric functions: the sine, the cosine, and the tangent. We'll look at the other 3 next. They're very related to these 3 here. So we can define the trig functions in terms of an angle t and the lengths of the sides of the triangle. So over here we've got angle t. It's over here, it is this acute angle. So notice that the other 2 angles that are not the right triangle will always be acute angles. And we also know that we have 2 right triangles, so here's another right triangle, and it's clearly much smaller than this other one, and I know that this angle is t, well, then I also know this other angle as well. In fact, it should be 90 degrees minus t, or we could say pi over 2 minus t, but we can always find that third angle. Similar triangles will always have this relationship where if you kind of stretch them or shrink them, the angles will all stay the same, but we're also just stretching or shrinking each side by the same factor. So that'll come into play as we talk about some stuff here. Let me get rid of some of these scribbles. But if we have this angle t and we want to know what is the sine of this angle t, well, that's going to be the relationship between a few of these side lengths here. So let's just get some terminology under our belt. Well, first maybe we should talk about the hypotenuse, because the hypotenuse should be the clearest one on here. It's the one that is directly across from the 90-degree angle. Hopefully you know what the hypotenuse is from things like the Pythagorean theorem. In fact, we're going to be using that a bunch going forward. It shows up in trig certainly, but in pre-calculus and calculus and for the rest of your math careers, it's just a very helpful tool. So we've got the hypotenuse there. Now we want to find the adjacent side. So if I'm looking for the adjacent side to this angle t, it is the one that is closest to it. So the one that's closest, that's not the hypotenuse, because one of them will always be the hypotenuse. Since we've already ruled that one out, we know the adjacent side is right here. And then if we're looking for the opposite side, then that is the one directly across, directly opposite from this angle. So I think hypotenuse is usually pretty clear, and opposite is usually pretty clear. It's the adjacent side that sometimes there's some issues with, but it is just the closest side that is not already the hypotenuse. So let's go through and define what each of these trig functions is. So if I want to find the sine of this angle t, what that is telling me, the definition, this is just what we're told, that it is the ratio of the opposite side to the hypotenuse. So whatever those angles or whatever those side lengths happen to be, we will look at those ratio. Look at that ratio, and that will be the sine of that angle t. If we wanted to know the cosine of this angle t, then we would look at the ratio of the adjacent side to the hypotenuse. So just kind of flip-flopping, instead of looking at the hypotenuse, or I'm sorry, the opposite and the hypotenuse for the sine, for the cosine, for the cosine, we're looking at the adjacent side and the hypotenuse. So just kind of sticking with the hypotenuse and the denominator there of that ratio, but flip-flopping what the numerator is. And then for the tangent, this is defined to be the ratio of the opposite side over the adjacent side. Oops. So here we are not considering the hypotenuse, but we are just looking at that ratio of the opposite side over the adjacent side. And you might notice this weird looking bunch of letters at the bottom here, and if you say them out loud, they say SOHCAHTOA, and that is our number 1 mnemonic device to try and remember what all of these ratios are, because these are just definitions. There's no way to figure these out. This is just the rules of the game. This is just what we're told. Sine is the ratio of the opposite over the hypotenuse, cosine is the ratio of the adjacent over the hypotenuse, and tangent is the ratio of the opposite over the adjacent. So this mnemonic device, SOHCAHTOA, can be really helpful. You'll hear it a bunch. I'm sure you might already be familiar with it from just culture. It is a pretty well-known thing here. So we will use this going forward to actually find some answers here. So here we are given an example, and we're asked to find the sine, the cosine, and the tangent of this angle alpha over here. So remember that we'll use different Greek letters usually to define or to use as variables for our angles here. So if I want to find the sine, that's going to be the ratio of the opposite side. So if I'm looking for the sine of alpha here, that's going to be the ratio of the opposite side, which is 8, over the hypotenuse, which is 17. So the sine of alpha in this case is 8 over 17. If we would like to find the cosine of alpha, that is going to be the ratio of not the opposite side, but the adjacent side, which is 15, with the hypotenuse, which is 17. So here we have the cosine of alpha is the ratio of 15 over 17. And if we would like to find the tangent, oops, let me do that a little better. If we'd like to find the tangent of alpha, this is going to be the ratio of the opposite side, so that's still 8, this time over the adjacent side, which is 15. So now we know that the tangent of alpha is the ratio of 8 over 15. Not much more to it than that. I mean, this will lead us into a lot of other stuff, and I think a natural question is, like, okay, well then what the heck is alpha? Can we use these relationships to figure out what that angle is? And yes, we can. We will get there as we go forward. But right now we're just trying to get comfortable with these definitions of sine, cosine, and tangent. You could also, I didn't say them here, but use this this mnemonic device, SOHCAHTOA, in order to kind of get these quickly if you don't have them listed out here with the definitions. So, all right. Next, we will look at the next three, the other three, I guess maybe I should say. There is only 6 total of these trigonometric functions, and that's the reciprocal trig functions. So we saw the sine, cosine, and tangent, and now we're going to look at the secant, the cosecant, and the cotangent. And these are very related to the ones that we just saw because they are just the reciprocal of the ones that we just saw. So if you remember, what we had on the previous page was that the sine of whatever angle t is opposite over hypotenuse, and here we see that the cosecant is just flipped upside down, the hypotenuse over the opposite. So these are reciprocals. This is the reciprocal of the cosecant of the sine function. Cosecant and sine are reciprocal functions, and you can see that right here, that the sine of t is the reciprocal 1 over the cosecant of t, and cosecant of t is equal to 1 over sine of t. So we can use that relationship going forward. We'll be looking at a lot of trig identities in the future, and these can be helpful relationships. And then if we notice here that we've got the cosine is just the reciprocal of the secant, or the secant is the reciprocal of the cosine function, and then we've got that the cotangent and the tangent are reciprocals of each other. That's the only one that like kind of makes sense in terms of their names, that the tangent and the cotangent are reciprocals. You would think that maybe the secant and the cosecant would be reciprocals, but they are not. They are tied to the sine and cosine. I also just want to point out here that reciprocal trig functions are not the same as the inverse trig functions. So reciprocals are multiplicative inverses, but they are not functional inverses for these here. So we will take a look at inverse trig functions later on, but I at least wanted to point that out right now, that these are reciprocal functions, but they are not inverse trig functions, at least not in the functional sense. Okay, so here we're given another example, and here we're just asked to find all 6 trig functions evaluated for this angle alpha here. So we will start with sine of alpha. We can use our mnemonic device. So if I want to find the sine, that is the opposite over the hypotenuse. So we're looking at the opposite, which is 4, over the hypotenuse, which is 5. So the sine of alpha here is 4 over 5. If I would like to find the cosine of alpha, that is going to be, so the mnemonic device there, ca, is the adjacent side. So the adjacent is the one that's next to it that's not the hypotenuse. So we've got 3 over the hypotenuse, which is still 5. So there we've got the cosine of alpha. Next we will find the tangent of this angle alpha. And that is going to be, that's the TOA. Whoops, I'm starting to write a tau. TOA. So that's going to be the opposite side, which is 4, over the adjacent side, which is 3. So we've got the main 3 here, the sine, the cosine, and the tangent. And we could go through and think about, okay, so cosecant, that's the inverse of the sine function. So should we just do hypotenuse over opposite? And we could, but since we already have these relationships here, and I know that the cosecant of alpha is just the reciprocal of sine, then we get these other ones for free. I'm just taking the reciprocal of the sine function, and I know that that will give me the cosine. And I can do that with all of them, so that's what I'm going to do. I know that the secant function is the reciprocal of the cosine, so I'm just going to take the reciprocal there and write 5 over 3, just looking at the reciprocal of that fraction. And then the cotangent is the reciprocal of the tangent function, so that will give us 3 over 4. So there we go. We've got all 6 of the tangent functions evaluated for this angle alpha. Yeah, and we really just need to focus, and that's maybe why I call these ones the main 3, because as soon as you get the main 3, we get the other 3 reciprocal ones for free there as well. All right, next we're going to look at these special relationships for 30, 60, 90, and the 45, 45, 90 triangles. So remember that if we know one angle here, it's always going to be 90 degrees. And if this one over here is pi over 4, then we automatically get the other one over here also being pi over 4. So that means that we have an isosceles triangle here. So if you think back to things that you learned in geometry, if you have a triangle that has 2 equal sides, and we know that the sides are equal because the angles opposite are equal, then that tells me that if I call this side length S, whatever it happens to be, then this side length over here will also be S. It's an isosceles triangle. By definition, 2 of the sides are the same, and the third one can be whatever it wants. It might be the same, but it's probably different. So let's take a look here at what we get. Since this is a right isosceles triangle, which will always be this 45, 45, 90. We're going to use the Pythagorean theorem. So if I want to figure out if there's some sort of relationship to this other side, which we'll call C, well, that's going to be S squared plus S squared is equal to C squared. So if I do some simplification, take the square root of both sides, so taking the square root of both sides, I'll get that C is equal to the square root of 2 S squared. And if I simplify that radical there, we get that C is equal to S times the square root of 2. So C, now we know, is S times the square root of 2. And that's a nice relationship to know. We're going to see a lot of 45, 45 triangles pop up as we go throughout this course. And now if we know one side, we can figure out the other 2 sides very easily by just using this relationship. That the equal sides should be the same, and then the hypotenuse here should be that side times the square root of 2. Okay, let's take a look at this other one here, the 30, 60, 90. So here we're trying to figure out if there is some maybe relationship between, I don't know, I don't want to say anything's called S yet, but you know, if we call this A, B, and C, if there's any sort of special relationship between these, and there is, if we can figure out something about those side lengths. So the first thing I'm going to do is not look at this triangle, but I'm going to look at an equilateral triangle. So an equilateral triangle looks something kind of like that. And we know that each angle in an equilateral triangle should be 60 degrees. Since every side length is the same, every angle is the same, there's 180 degrees total. Divide that by 3 and you get 60. So we've got that. The next thing I'm going to do, I'm just going to erase my 60 up here because I'm going to want to drop a line right down the middle, and I'm going to cut that right in half there. But as I do that, I'm creating a couple of right triangles here. There's one on the left and there's one on the right. And since this was an angle of 60 at the top, and I just split it in half, I know that these are both 30-degree angles now at the top. So now we can see that we've got a couple of 30, 60, 90 triangles. So this is what we're going to use to find some relationship just in general here. So we've got this entire side length down here, and I'm going to say that each of these little shorter sides here is called S. So that the entire side length here is 2S. So just that short little bit across from 30 degrees is called S. Each one of those is called S. And if we add those together, we get 2S. Since this is an equilateral triangle, I know that every side here must be 2S. So that gives us our first relationship here, that if this shorter side here, the one that's across from 30 degrees, since 30 degrees is the smallest angle, that tells us that the one across will be the shortest side. So if that is S, that tells us that the hypotenuse over here must be 2S. So we get that relationship from looking at the equilateral triangle. If I want to figure out what this last bit is, we'll call it h for the height of the triangle. We can call it any variable we want, but we'll just use the Pythagorean theorem again, that here we're going to get s squared plus h squared is equal to 2s quantity squared. We're trying to solve for h here, so let me maybe simplify. On the right hand side, I'm going to get 4s squared, and if I subtract s squared from both sides, we'll get that. And if I take the square root, and we're going to get h is equal to the square root of 3s squared. And then I can simplify that bit, and we'll just get s times the square root of 3. So now we know that this other side here, the longer of the two legs of this right triangle, is s times the square root of 3. So we now have these two special relationships here. Let me just kind of scoot that down a bit. These two special relationships here for these right triangles, for the 45, 45, 90 and the 30, 60, 90 triangles. As soon as we know one side length, we can use this relationship to find all the other side lengths. So we are going to use what we just learned about those special triangles to evaluate our new trig functions at some of these special angles. So remember that here I've switched back to using radians, because going forward we'll be using radians more than degrees, but I've been kind of just been sticking to degrees a little bit, so some of those proofs make sense for why we're getting what we're getting. But here we're looking at radians, so remember that pi over 3 is the same, whoops, I'm already writing the wrong thing, that pi over 3 is the same as 60 degrees, and pi over 6, which is half of pi over 3, is 30 degrees. And that pi over 4 is the same as 45 degrees and 45 degrees. So I'll just write those there as reminders if you find them helpful, but we will be writing a lot of radians going forward. So what we want to do here is find the sine of pi over 3. So we're just going to use the relationships that we know. We know that, maybe if I write just over here for now, so, ka, toa, we can use that. And then maybe I'll erase that once we need to write things in over there. But here I want the opposite over the hypotenuse. So if I'm looking at pi over 3, I want the opposite side here, which is going to be s times the square root of 3. So I'm just using that relationship that we know. And then in the denominator, we're going to have the hypotenuse, which here is 2s. Oops, 2s. Well, here we see that the s's cancel. And what we're left with is just the square root of 3 over 2. Now we know that the sine of pi over 3 is always the square root of 3 over 2. And that's good, because we want sine to be a function. And if pi over 3 was sometimes square root of 3 over 2 and was sometimes something else, then that wouldn't be a function. So we get that because of similar triangles always having the same ratio of side lengths, that ratio is going to be the square root of 3 over 2. Okay, let's take a look at the cosine then. So the cosine is going to be the adjacent side. So here the adjacent side is going to be just the s over the hypotenuse, which is still 2s. Oh, here we get to simplify again, and we have that the cosine of pi over 3 is just 1/2. That will always be the cosine of pi over 3. For any triangle that we're looking at, or any just angle that's not part of a triangle. If that angle was measured at pi over 3, we take the cosine, we get 1/2. All right, looking at the tangent next. If I want the tangent of pi over 3, that is going to be the opposite over the adjacent. So the opposite here is s times the square root of 3. And then the opposite, I don't know what I just said. The opposite is s over the square root of 3, s times the square root of 3, and the adjacent side here is s. So here the s's cancel, and we have just the square root of 3. So now we know the tangent of pi over 3 is always the square root of 3. Of course, we could put these into a calculator and find them, but you know, how does the calculator know what they are? How does it know what they are and how to find them? So this is kind of more or less what we're showing here by hand. So now that we've got kind of the main 3 here, we get the other reciprocal functions for free. They're not in exactly the same order, I'm noticing now. So remember that the sine and the cosecant are reciprocal functions. So maybe I'll start with those ones there. So if I'm going to write the cosecant of pi over 3, then I'm going to take the reciprocal of the sine and get 2 over the square root of 3. Now we will rationalize the denominator there. We'll multiply by the square root of 3 over the square root of 3, and we get 2 square roots of 3 over 3. So that is the value of the cosecant at pi over 3 every time, because those relationships between the sides of those right triangles will always be the same. Taking a look at the secant here, the cosine and the secant are reciprocal functions. So if I take the reciprocal of 1/2, I get 2 over 1, which is just 2. Now I know the secant of pi over 3 is always 2. And then we'll finish off here with the cotangent. So that is the reciprocal of the tangent function. So we had just the square root of 3, so the cotangent is going to be 1 over the square root of 3, taking that reciprocal. We will rationalize our denominator, multiply by square root of 3 over square root of 3, and we get the square root of 3 over 3. So there we go. We've got all of the trig functions, all 6 of them evaluated for pi over 3. So pi over 3 is going to be a very common angle, so is pi over 6, and so is pi over 4. So that's why we're looking at these ones here. For the pi over 6, we're not going to look at the reciprocal functions, but I do want to just notice maybe a nice relationship that is popping up here. So for now, we're just going to take a look at the sine, cosine, and tangent for pi over 6. So now we're going to be focusing not on that bottom left angle, but on this top angle up here. And so now when I'm looking for the sine, the opposite over the hypotenuse, here the opposite is going to be s, and the hypotenuse is going to be 2s. Those s's cancel, and we get 1/2, which at first you might be like, hey, wait, we already have 1/2. That was the cosine of pi over 3. And hopefully that makes sense that we're getting the same thing because we're using the same triangle and using the same side length relationships. We're just changing the angle, which changes the ratios of these, or the numerator and the denominator in these ratios. So let's take a look at this next one here. We'll look at the cosine, the cosine of pi over 6. That's going to be the adjacent side. So here the adjacent side is s times the square root of 3 over the hypotenuse, which is 2s. And again, the s's are going to cancel, and we're left with the square root of 3 over 2, which again, we found up over here. It is the same as the sine of pi over 3. And again, that might seem surprising at first, but if we think about it, we're again just using the same sides of the same triangle. We're just doing them kind of in a different order here. And then we'll take a look at the tangent. That's going to be the opposite over the adjacent. So if we're taking a look at the opposite, which is going to be s, over the adjacent, which is going to be s square roots of 3, the s's cancel, and we get 1 over the square root of 3. We'll rationalize that denominator, and we'll get 3 over, the square root of 3, almost there, square root of 3 over 3, which we did see as well is the same as the cotangent at pi over 3. And this is, again, no coincidence. It's because these are using the right triangle no matter what here. And we're going to investigate kind of this this cofunction evaluation relationship here in just a little bit. So keep that in the back of your head, but I want to look at the pi over 4s here as well. So if I'm taking a look at sine of pi over 4, so now I'm using the bottom triangle here. We're done with the 30, 60, 90. So the sine is still the opposite over the hypotenuse. And here I can pick either one because they're the same angle. So here I'll just pick this bottom one just so we can pick one. But I want the opposite side, which is going to be s, over the hypotenuse, which is s times the square root of 2. Oops, square root of 2, not the square root of 3, square root of 2. The s's will cancel, and we'll want to rationalize the denominator. We will be rationalizing a lot of denominators. And here we are going to get the square root of 2 over 2. So that is the sine for pi over 4 every single time. The cosine for pi over 4, again, if I clear off my triangle here, here we want the adjacent side. Oh, look, that's still s over the hypotenuse, which is still s times the square root of 2. And we're going to get the same thing here. So we got the exact same result. I won't go through the rationalizing process there. We get the exact same result. Square root of 2 over the square root of 2. So, and hopefully that's not surprising since we're always looking at the ratio of, adjacent and opposite sides that are exactly the same over the hypotenuse. We're not shocked that we get the same value for both of those there. And then taking a look at the tangent for pi over 4, that is going to be the opposite over the adjacent, which is always s over s, which is always 1. So we will see that the tangent of pi over 4 is always 1. So a smattering of some of the more popular angles that we will see throughout your trig and pre-calc and calculus careers here, evaluated at the different sine functions. I'm not saying memorize these all right now. I think as you do a lot of work, a lot of these will begin to stick in your mind, and especially once we get to looking at these trig functions being defined by the unit circle, I think that memorization becomes not something that you need to do at that point. So for now, notice these numbers. You're going to see these numbers pop up a lot as we go forward, since they are the trig functions being evaluated at these super common angles. So. All right, let's take a look at these cofunction identities. So like we saw in that previous slide, we saw that some of these trig functions have the same value at complementary angles. I didn't use that word complementary before, but we know that they are complementary angles. So we were looking before that, let's say if alpha is pi over 3 in this example, and beta is equal to pi over 6. Those add up. If you add those together, you would get pi over 2. And I don't have to think about that too hard because I know that one of these angles is pi over 2. I know that the total angle measure in the entire thing is pi, which is the same as 180. I'm thinking in radians here. We got to start thinking in radians. And if I add those together, if I add everything, all these angles together, I should always just get pi. We always know that one of the angles is always pi over 2, so the other angles should be complementary, meaning they add up to pi over 2. I was just writing in some specific angles there, but they can be arbitrary. So, what I was just saying was sine of pi over 3 is the same as cosine of pi over 6. Those are complementary angles, and they have the same output. Same thing with sine of pi over 6 and cosine of pi over 3, because those are always the ratio of those same sides. That will always be 1/2. So we get these cofunction identities that if, or just the fact that if we've got these angles alpha and beta, that the sine of alpha will always be the cosine of beta, and vice versa, that the sine of beta will also be the cosine of alpha. So here we have the cofunction identities written out in radians, but I want these to make sense because I don't, you could just memorize these and remember that it's always pi over 2 minus t. But that is happening because if I take this angle here, if I call this alpha and we call this angle beta, we should see that t, alpha, plus beta, pi over 2 minus t, is equal to just pi over 2. These angles are complementary, so these are all exactly the same, but if you add t to pi over 2 minus t, you always get pi over 2. That's the reason that these cofunction identities are set up the way that they are. So you don't have to memorize them as long as you understand that, oh no, I'm erasing a lot of stuff here. As long as you understand that complementary angles have these cofunction identities, then the formula should be right up there at your fingertips. So just pointing these out here, writing them down might help them stick in your brain a little bit better, but the cosine and the sine functions are cofunctions of each other that we saw on the previous page. And we also saw that the tangent and the cotangent were also cofunctions. So we saw that as well with this square root of 3 over 3 and the square root of 3 over 3. And then we see that the secant and the cosecant are cofunctions, and that hopefully is not too surprising. They're the reciprocals of the sine and the cosine function, so the fact that those are just kind of shifted by pi over 2 is not too surprising as well. But there we go. We've got all of these cofunction identities, and we can use them to solve problems as we go forward. All of these things that we're learning here are all just tools that we can put in our toolkit to help us solve problems as we move forward. Speaking of which, here is a problem that we are asked to solve. So here we're given just a few pieces of information about this triangle, and we're asked to find all of the other information. We're asked to find an exact value for each. So let's see if we can't do that here. So what I'm noticing here is we've got this angle, 30 degrees, and I know what the opposite side is. So let's first maybe pick a side to solve for. We'll start if we can solve for A here. So side A, just write this down. I know that the opposite side is 7, and what we're trying to find here is the adjacent side. So is there anything that we know that relates the opposite side to the adjacent side? And hopefully we are familiar with this tangent function now, and we know that the tangent of alpha is the ratio of the opposite side to the adjacent side. So we can use this to see if we can't solve that missing piece. So what we have here is that the tangent of 30 degrees is equal to the opposite side, which is 7, over the adjacent side, which is what we're trying to solve for. So from here, we can just do a little bit of algebra, multiply both sides by a and divide by tangent of 30, and we'll get that a is equal to 7 divided by the tangent of 30 degrees. So at this point, you just have to put this into a calculator. I mean, I suppose we know the tangent of 30 degrees. We saw that for the pi over 6, but just putting that into a calculator will get us what we want here, and we would see that that is going to be about 12.1. So we can use that for right now, but we were asked to give an exact value. So maybe we'll come back a little bit later and think about how we can get an exact value here, but this method does work for an approximation. So that is why I'm modeling this one first, and then we'll go back and think about the exact value method. Okay, now if we want to solve for this side C over here, so for side C, here again, we know that the opposite side is 7, so we know something about the opposite side, and here the side that we're asked to solve something for is the hypotenuse. So is there any sort of relationship that we know, any sort of function that gives us relationship between the opposite and the hypotenuse? And that is going to be the sine function. So the sine of alpha is the opposite over the hypotenuse. Now we can plug some things in that we know here. We're looking at the sine of 30 degrees. We know that the opposite side is 7, and we are trying to find the hypotenuse here. So do a little algebra again, and we'll see that C is going to be equal to 7 over the sine of 30 degrees. You'll go put that into your calculator, and you will see that C is equal to 14. We get an exact value out of that one, which may seem surprising at first, but remember that the sine of 30 degrees is 1/2. So maybe we're not too surprised. So here we actually do get an exact value. We know that C is equal to 14. Okay, so now let's go back and think about this side A here, because we were asked to find an exact value. Well, we also know that 30-60 triangles have a special relationship where if we know one side length, we know all the side lengths. So we could have used that from the beginning here. We've got a 30-degree angle over there, which means we have to have a 60-degree angle over here for them all to add up to 180. Now I'm not surprised if we call this short side here, S, that the hypotenuse, C, should be 2 times S, 2 times 7, which is 14. Hey, how about that? Math is consistent. We get the same answer either way here, which means that the other side length here should be S, which is 7, times the square root of 3. So now we have it as an exact length, not an approximation, but A is exactly 7 times the square root of 3. So this exact method thing here is only working because we have a 30, 60, 90 triangle. But what the work I did here in the green and the yellow, where I'm using the tangent and I'm using the sine and I'm putting those values into a calculator, that will work for any right triangle. It doesn't have to be a 30, 60, 90. But we can also find those exact side lengths here because it is a 30, 60, 90. All right, next we're going to take a look at angles of depression and elevation. So these are just some terms we're learning so that we can use them to solve application problems. So I wanted to take a second and talk about what each of these are before you're expected to just use them to solve some application problems. So the angle of elevation refers to the angle whose initial side is some kind of horizontal baseline. So what we're saying is that we're down here on the ground. We are the observer and we're down here on the ground. And our initial side is just the ground here, or just our line of sight at the ground if we want to kind of approximate. And the terminal side is just the line of sight up here to our object. So this angle is the angle of elevation. We are on the ground, we have our line of sight going horizontal, and then we're looking up, and that angle created by the ground and our line of sight is the angle of elevation. Similarly, we have the angle of depression. So now we are no longer on the ground. Now we are up at the top of this building or whatever. We are up here, and our initial side now is not the ground, but it is just our line of sight. Our line of sight going out that way, that's supposed to be a horizontal line. I did my best. Oh, I should just sketch it in then. So we get this horizontal line going out that way. And now the angle of depression is the sine of our line of sight as we're looking down at some object that's on the ground down here. That one's a little bit better. So now here we get our angle of depression. So what maybe I first want to notice is that the angle of depression is not this inside one. It's not the inside angle that might be, completing this right triangle that we're looking at here. That is not the one that we're looking at. The angle of depression is this other one on the outside of the triangle that is being created with this building or whatever this thing is here. So that is one important thing to notice. But another important thing to notice is that since the line of sight are both horizontal, for both initial sides here, that means that the angle of the depression and the angle of elevation are equal. So we can use that relationship to help solve some problems here. So now we have the angle of elevation defined and the angle of depression defined. We can use those to solve some problems. So here is one to solve. We are looking to find the height of a tree, and we're told that, I've got some scribbles left on here from when I was setting this up. We want to find the height of this tree. So a person walks to a point 30 feet from the base of the tree. So this person wants to know how tall this tree is. They're starting at the base down here, and they're walking out, and they're measuring a distance of 30 feet. And then they look up at the top of the tree, and they have some way to measure this. So, you see surveyors and stuff. They have ways to measure angles. Looking up here, and they find that there is a measure of 57 degrees. So that is the angle of elevation. This is an angle of elevation. So we want to find the height of the tree here. So I can just drop in a 90-degree angle, and we want to find, I don't know if it shows up okay there. We want to find this length h, which will give us the height of this tree. So let's think about what we have here. We have some angle, and we know what not the opposite side is, but we know what the adjacent side is. We know what the adjacent side is. And we are asked to find something about the opposite side. Well, this gives us the cotangent, so maybe I just flip these around. So I have opposite over adjacent, and this is the tangent of alpha. So I could have used the cotangent, but I have a tangent button on my calculator that's available and ready to use without having to shift to anything else. So I started just thinking about this problem, and I had the adjacent and opposite. That wasn't quite what I wanted. This will give us the cotangent, which is fine, I suppose, but the tangent is a little bit more familiar, so that's the one that we'll use here. So what we are seeing is that we have the tangent of 57 degrees is equal to the opposite side is h, and the adjacent side is 30. So doing a little algebra here, we'll multiply both sides by 30. We get that h is equal to 30 times the tangent of 57 degrees. So we'll go put this into our calculator, and we'll see that h is approximately 46.2 feet. So there we go. We are able to tell how tall this tree is. Now, I should maybe take a second and point out that if you're trying these problems along with me and you're putting things into your calculator and you're not getting the right answer, make sure that your calculator is in degree mode. Right here, we are measuring these angles in degrees. And that means that your calculator needs to know, it needs to be told that you're putting in these angles in degrees and not in radians. Moving forward, we might want to make sure that our calculator is in radians and not degrees. I think that is the number one reason to make mistakes or think that you're getting things wrong in a trig class is just because you put things into a calculator, you're not getting what you expect, and it's just because your calculator is in the wrong mode. So make sure that your calculator is in whatever mode you need. If it's degrees, make sure it's in degrees. If it's radians, make sure it's in radians. The other one is called gradians, which I've never had to use and has never shown up in my life. I think that is splitting the circle not into 360, but into 100 units, which maybe makes more sense to us. I might be wrong there. You can double check me and let me know if I'm wrong, but I'm pretty sure that gradients are splitting the circle into 100 pieces instead of 360. So we won't be using that one, but make sure that your calculator is in the right mode here, and we should hopefully get the right answer. All right, with that, it looks like it's time to go practice. So good luck. Let me know if you have any questions, and I'll see you in our next video.